Hello everyone, my name's Callum and I'm here to give a brief introduction to SpatialOS, the distributed games platform built by Improbable. Today we're going to go over a brief introduction to the platform. I'm going to give you an overview of the terminology that we use surrounding the product. We'll talk specifics about what's available today, and I've also got a deep dive into distributed physics for you because I know you'll have questions about it afterwards. So just a little bit of information about us, Improbable. We started off in 2012. We've seen several rounds of funding, and so far we've managed to get in and around 20 games in development on our platform. So SpatialOS, the platform design, build and run games without limits. The three pillars that we talk to when we're talking about if a game is applicable or relevant for SpatialOS. The first being scale. So scale doesn't just mean dozens or hundreds of players. Scale can mean thousands of players, right? We add lots of zeros to those constraints. But it also means scale in terms of the amount of content you can have in your game, meaning that you can have bigger, more advanced, more meaningful worlds. Persistence is something that players are demanding more and more of in games, in modern games. And by persistence, what I mean is lasting impact from player decisions. So a player can actually have an effect on the world that lasts beyond the length of time of a play session. And finally, rich simulation. Now, I normally talk about this in terms of complexity. I don't just mean that there's more numbers, there's more AI, there's more physics going on. I mean that the complex interactions between all of those systems can be increased by unlocking compute using the cloud. So SpatialOS itself is it's not a new paradigm in terms of as a day-to-day gameplay programmer. So it's an entity component system which everyone should be familiar with. So Unity have their game objects and their prefabs. Unreal has its actor-based hierarchies. Ours is very similar. But the new term that we're introducing today is the term worker. Now, a worker is any process, any physical process built against our libraries that can connect to SpatialOS. So that could be a game engine, that could be a specialized physics process, it could be a specialized AI process. The thing to call out here is that a worker is not a thread, and it's not necessarily a server. A worker is something that could potentially be running on a server, but it's a standalone process. So authority, or SpatialOS uses an authority paradigm. It's very similar to a client-server architecture. The only difference with SpatialOS is now you're not the only server in town. You're not the only game engine simulating your part of the world. You may lose authority at runtime because SpatialOS has stitched the world together. So authority is one of the sort of head spinny things that you have to get your head around first. And then finally, the last term is runtime. So the runtime is our black box. It's our sort of like secret magic sauce. It's basically a JVM process we run alongside yours. And it's the thing that does all of the hard distributed systems stuff. It keeps the entity database in RAM. It orchestrates the workers that are required, and it ensures that there's no overlap or dropped messages or anything like that. Cool. So the best way to build a model in your head of what SpatialOS enables is to let's just go on an exercise, let's go on a journey together, and we're going to build a world. So step one of building a world with SpatialOS is we're just going to add an instance of that runtime that we spoke about earlier. Now, because everything we do at Improbable is distributed system friendly, you can add another one. The number of these that you'll need depends on the game type, it depends on the density, and we have lots of tools for helping you pick the number of runtimes. Then what happens is you guys define some entities. So it's an entity component system, you define the entities, you define, more importantly, the components on those entities, and you fill the world with those entities. And it's worth calling out, static and dynamic aren't hard-coded concepts in SpatialOS. This is just for visualization purposes. Obviously, on its own, that would be a relatively boring world. So now we're going to add some workers. So now what you've done is you've written a process that links against our libraries and implements our APIs. And now SpatialOS has launched 2 workers for you. Already, you now have twice the amount of power that one process would normally have. But obviously, a world is dynamic, things start to happen. As players join the world, the amount of compute needed goes up. SpatialOS as a platform can bring up more workers. We can bring up more compute, and thanks to the runtime, we can throw all of those workers and load balance them in a way that's sensible. So this is what a game world looks like on SpatialOS. Lots of workers simulating a single space that feels completely seamless to all of these entities. What you get out of the box, what the runtime actually does, the hard distributed system problems that we've solved. Firstly, those boundaries are seamless. Entities are completely unaware when they walk across a worker boundary or a runtime boundary. You've never had to write code, special edge case code, covering what happens when worker A loses authority on worker B. Obviously, as entities move around, the load that they take with them moves with them as well. So we have load balancing strategies that allow the workers to change as well. So it's a proper fluid environment. The entities are moving and the workers are moving as well. Distributed messaging, obviously in a distributed system with nodes going up and down, workers failing, it can be hard to guarantee anything, to be honest, but we guarantee certain levels of message delivery as well. So if an entity has the ID of any other entity, it can always try and message them. And that works across boundaries, that works across any edge case you can think of. Streaming queries. So one feature that you get for free, the thing to remember about SpatialOS is your entity component data is now stored in a really, really fast in-RAM database. Now, game engines wouldn't ever duplicate data for faster querying or faster indexing because they're all about optimizing the amount of RAM used. The thing about a database is that it's incredibly efficient to query a database. So what I've got here is 3 clients, and although they've only queried the database for a small area around them, adding a global entity that these clients get updates from in real time is very, very simple in SpatialOS. It's simply the act of changing the query to check out entity ID 50, which represents the boss. So you get this incredibly efficient query structure, which helps unlock new types of gameplay. So under the hood, what are we actually running on? Obviously, one of the really cool things about SpatialOS is we're cloud agnostic. So at any given point, your game could potentially be running on Google, Amazon, or Azure. The actual topology is up to you. So in this instance, we've gone with, imagine you're 3 months into the project. You haven't had a chance to optimize your server-side processes as much as you'd like, but you have a meeting with a publisher and you want to ensure that that playtest is successful. So you can throw a load of hardware at it. You can throw 4 machines, 1 runtime on each, and all of your workers running on the other 2. Eventually though, obviously when you've decided on a cost profile and you've done all of your load testing calculations, you can then adjust that topology to make more sense for what the actual live game will look like. So everything in Improbable is distributed, including our node layouts. So the concept of a deployment is obviously a new concept. Some people call it an instance or a game world. For us, it's difficult because there's lots of terms conflated within a deployment. So a deployment on SpatialOS is backed by multiple instances of your game engine, as well as multiple machines. So we're not just talking about a server anymore. We're talking about potentially dozens, if not hundreds of servers working together. So I like to think of a deployment as a game world. It is a world that exists in the cloud. So we've got a worker API. The same API you write your server-side code against is the same API you write your client-side code against. Now, the important thing to remember is your clients, your mobile console or PC games, they're no longer connecting directly to a game engine. They connect to our runtime. So the runtime forms like a man in the middle. And what they do is they just query the world around them. And get real-time component updates around the player entity or in whatever view that you want the player to have. And the really cool thing here is that cross-screen play becomes completely native and completely possible. So your high-fidelity PC game could be interacting with a lower-fidelity mobile game. And potentially, if you wanted to build the most expensive game ever, they could be using different game engines. You could have an Unreal PC game interacting with a Unity mobile game, backed by a C++ worker in the cloud, as well as a C# worker in the cloud. So the thing to drive home here, and the thing to really take away from this presentation, is that there is only one API for SpatialOS. The fact that you can mix and match C++, Java, and C# means that you can start modularizing features, adding and iterating on complexity and new systems in a way that you couldn't do with a normal game engine. But obviously, we do support all of the normal game engines too. So, as a rough sort of overview of how the infrastructure works, we have what we call clusters. So we have several EU clusters, several US clusters. We have one cluster available in Asia today, and we're currently partnered with a gaming firm called NetEase, and we're working with them to find a cloud provider in China. But we have a global login service, so this would be somewhere where you would implement your Steam authentication or your PlayFab authentication. If you have your own account system, we can integrate with that as well. And then obviously what happens is your clients will ping our login service, we'll validate that token, and we'll forward them onto the deployment that you've requested for that client. So to recap, because I know that was a lot of information, we sort out all of the serialization across the boundaries for you. Your entities are completely unaware that they're in a distributed system. We help with distributed load balancing. We have load balancers you can use today, and you can also write your own. We support completely distributed messaging. Any entity with any entity ID can send a message to any other entity at high latency as well, at low latency as well. So if you've got, if your headshot is an RPC, then that's absolutely fine. We support really efficient queries, and that's able to run on multiple different types of hardware, user configured topology, and we obviously support multiple deployments. And the big thing to take away is there's just that one API. Once you get your head around that API, that's it. You can now write server-side code, you can write client-side code, you could write a load balancer. Cool. So what's actually available today? Like if you sign up to SpatialOS today, what do you get out of the box? So we have several layers. At Improbable, we strive to write as much C++ as possible. But we understand that some developers don't necessarily want to write that, and also some engines don't support C++. So from a technical point of view, we marshaled all of that memory management through a C layer, and we offer a public C layer, a C++ SDK, a C# SDK, and a Java SDK. The really cool thing about these is our Unreal and Unity products use those low-level language SDKs. And any fix, any bug that's found in the public-facing SDKs get fixed in the lower-level core SDK, which is super nice. When you're configuring a database, like a normal database, you'd have to give it a configuration file, like a schema of sorts. So we have our own schema lang to configure your in-RAM database. So on a day-to-day basis, the thing that changes most for a gameplay programmer is you're no longer going to the top of your class and defining variables like m_health and then serializing them yourself. In SpatialOS, what you do is you go to schema first, you define that you want a synchronized message, a synchronized property, or an event that you can trigger that gets publisher subscribed to everyone listening. You define that in schema. We give you a code generator that supports C++, C#, and Java, or native Unreal or native Unity. And from schema, you generate all of your networking stack. So SpatialOS comes with UDP transport protocol. We also support TCP and KCP. So you don't need to write a network protocol, but what you have to do is configure your in-RAM database in schema lang. So obviously we have a Unity GDK, which is relatively new. It's still in alpha, but it's gaining traction. We've got some really cool features coming out. We already have the ability to run both a client and a server in the editor at the same time, which is becoming really useful for fast iteration. And there's a 200-player FPS starter project, which is available now. And we have an Unreal GDK as well. So this supports, in Unreal, this supports native replication. This is a truly native experience for Unreal. If you have an actor in your scene and you tick box replicate on a property, that will just work. We have our own branch of Unreal, which you have to build against. But after that, it is just a case of drag and drop and use Unreal in the way that you understand already. So one of the main problems when you're running more than one game engine stitched together is this idea of this it's a spatialized problem and it can be hard to visualize. So we've actually built a visualization tool that supports several hundred workers and millions of entities. And what it allows you to do is very quickly assess where there are problems and if there are problems. It's great for monitoring a live game as well. But this is like our go-to debugging tool. It runs locally as well on your machine when you're just in development, but it also runs in the cloud. Distributed logs, obviously when you're running hundreds of copies of your game engine, you do get a lot of logs. And most of the time you just want to know what happened to one entity across several processes. So we aggregate all of those log files across multiple instances of your game engine, and we put them in a very nice front end that allows you to very quickly drill down into the problem that you're looking for. The same with metrics. Most network engineers love our metric stack. We track almost everything by default, but we also support custom metrics. So when you're profiling in the cloud, it can be difficult because you've got 10 instances of your game engine and they're all potentially doing 10 different things. This metrics platform allows you to get a very good high-level overview of where the compute is being spent, where the bandwidth is coming from. We've got breakdowns per field, per command as well. Spatial Cloud launch. So obviously we are in all senses a cloud platform, but we're agnostic to which actual cloud platform we work on. So we have a wrapper, we ship you a tool, we allow you to upload to us in a secure way and launch a deployment on a cluster. The really cool thing here is a global deployment script on SpatialOS is less than 20 lines of C#. You can see here, this script will bring up 6 deployments, 2 in the EU, 2 in the US, and 2 in Asia. With China support coming really soon. So no more worrying about AWS or Google changing their APIs or their support. We've wrapped it and we have backwards compatibility guaranteed. Other tools you get out of the box, obviously, when you're running in the cloud, we have a console, which is like a really good holistic overview of what's actually running. You can quickly share a link to any deployment with temporary auth access. So a lot of people use this for sending in an email to a publisher, or if there's a potential investor, or if you just want to put it on our forums and get a playtest and get some early feedback, we can share a link to your deployment. And it will download the client binary, and you'll be able to run get a couple hundred people in a playtest really quickly. We've got some super advanced debugging tools. We're just about to roll out support for SSHing into the box. Unreal Crash Dump support is coming soon as well. And what's really awesome is we have this live data changes. We call them flags with a Z, but you can have your workers subscribe to a distributed key value pair that on the console you can edit at runtime. So if your designer or your creative director isn't quite sure of what the run speed should be, you can use a one-line code change to listen to a value that they can then go tweak. So mid-playtest, if you decide that the jump height is too big, you can just lower it and see if people prefer playing it. So it's really good for that quick iterate cycle. Snapshots. I've already mentioned some of the benefits of keeping all of your data in an in-RAM database, such as the really efficient ability to query that data. Another really cool thing that comes out of that is the ability to just grab a complete copy of the database at any point without any real runtime performance impact. So the way it works in SpatialOS is by default, your entire world is snapshotted once a minute into a file blob, which you can then download. Now you can turn those blobs, these snapshots, into JSON, and if you wanted, you could run some analytics over the top of that. So we think there's huge potential here for figuring out not just heat maps of where people spent their time, but heat maps of where people were looking, how much health they had on average, what events were triggered more often than others. There's potential here for a huge amount of analytics. Cool, so I understand that was a lot of information. Obviously there's lots of tools out of the box, and SpatialOS's offering is pretty broad, but a really common question is, how does it work in the overlapping bit, the bit in between two workers? How does an entity actually move across from one boundary to another in a way that is seamless, right? How as a gameplay programmer, what code am I writing to make that happen? So let's do a deep dive. So I'm going to ask you to focus on worker 0, so the blue worker in the bottom left-hand corner, right? We're going to pretend to be entity ID number 5. Now, what happens when entity ID number 5 starts moving is you'll notice that worker 1, the yellow worker, already had access to entity ID number 5, but he only had read access. What that means is when worker 0 was changing the position of entity ID number 5, worker 1 was getting told about it. Now, the latency between worker 0 and worker 1, on average, on the 99th percentile, in a good cloud platform, is sub-millisecond, right? There is, most advanced modern data centers have invested in a lot of hardware for inter-node communication, right? Driven by advances in machine learning and natural language parsing. And we're piggybacking off that hardware advancement by guaranteeing super low latency between workers. So at some point, entity ID number 5 will walk far enough into worker 1's area, and you'll see that SpatialOS will send both those workers messages. It will tell worker 0, hey, you're no longer authoritative, you've just lost authority, so move him back into read access. And he'll tell worker 1, hey, that entity you had read access on is now yours to command. So if that's a player entity and input messages are being sent up, SpatialOS will stop routing from worker 0 and start routing those messages to worker 1. I apologize that the authority cycle looks like the recycling symbol, but one of the hardest things about distributed systems is guaranteeing this level of consistency. And this is something that we guarantee. Authority will always cycle from has to loss imminent to no authority. No matter where you get injected into that cycle, we guarantee that you cycle fully around. The reason we do that is it makes the code you write against authority changes so much simpler. It provides an incredibly powerful abstraction. So that's what happens when entities change across boundaries. What does it look like to the client? So the thing to remember is authority isn't entity-based, it's component-based. So in reality, if a entity ID number 5 is a player entity, the way the client is communicating to that entity is they probably have write access on a component on that entity. So I've got this input component here, and the player worker is allowed to write to that component. When that component gets changed, worker 0 and worker 1 get told about it by SpatialOS. And that's the hard distributed system routing problem that we've solved. And obviously, as an example here, the thing that I really like about this is there are two clients. Their physics is being simulated by the same process. So worker 1 is authoritative on the physics and the position for player ID 5 and 4. What's cool about this is player ID 5 and 4 don't know about each other and obviously don't have each other checked out from the database. So they don't get told about each other when they change. The really interesting thing to note here is that worker 1 isn't doing any of that maths. Worker 1 isn't bothered or using any compute to work out that player 5 is so far away from player 4 that when player 4's position changes, he doesn't have to tell player 5. Worker 1 just has this very naive view. He just looks at the entities it's been told to simulate and simulates them. So area of interest is done by the runtime. It's done by SpatialOS using advanced and incredibly efficient queries. So if your game engine is, for example, Unreal doesn't have to do any of the replication condition checks, which can be very expensive when you've got lots of players in a small area. That work is now done by our runtime, which can do like incredibly advanced techniques to do with query aggregates and query broadening and other such distributed system things. The really powerful thing about authority being per component means that you can now start to layer systems in a way that make them easier to develop, easier to test, more parallelizable from a production point of view, and much more easy to reason about. So in this example, I've got a physics engine working on the physics components and a fire worker working on the fire components. Now you could unit test the fire worker much easier than you could do if it was a feature within a game engine. You could imagine the contract between fire and physics being an asynchronous component update. You could do an integration test at that layer. But the really cool thing is that the fire worker could be developed in complete isolation from the physics engine. And if the physics engine breaks, it doesn't break the fire worker. So this sort of modularization, this breaking apart the behemoth is what Improbable thinks is the future of the game engine. But the cool thing is that we're a mid-step as well, because we also support those game engines running in the cloud. So this is like what we think the future of game engines could potentially be. A single entity called a monster, which is actually simulated by 3 separate specialized processes. Each process is load balanced in a really particular, really fine-grained way. Each process is unit tested in a very specific, very fine-grained way. And because it's properly modularized, scaling becomes much, much easier. Under the hood, the way SpatialOS works is there's a known component that we ship, and it's called the access control list. And basically what this does is this pairs constraints with requirements. So when an entity gets spawned and its constraint is physics, SpatialOS will launch a physics worker. It's just a naive string pairing. You give us the command to run to bring up the worker, and you give us the string constraints to pair with that command. So SpatialOS orchestrates the workers, it launches the workers for you, and then runs the load balancer. Cool, so now that you understand how we move authority around in order to stitch the world together, let's talk about the hardest problem. The hardest problem that we've solved, physics, distributed physics. So I've got what we think is the worst case scenario. We've got 3 entities, ID 4, 5, and 6, and they're each being simulated by a different physics engine. So this could be Havoc, this could be PhysX, this could be, each one could be an instance of Unity or Unreal using their implementations of PhysX. And the worst case scenario is that they all charge into the middle of the overlapping region and all collide. So what does this look like? How does SpatialOS help solve this problem? The interesting thing is that you don't have to write any special case code in order to help solve this problem. You don't have to go into the definition of a rigid body and make it network aware. Because of the latency in between those workers, and because of the tick rate of the average game engine on the server side, 10 Hertz, 20 Hertz, 30 Hertz, what happens is this. Worker 0 will go into its broad phase. It will say, oh, I've got 3 potential collisions here. It will go into its narrow phase and it will say, yep, these 3 objects are definitely colliding. It then does the standard physics engine thing of working out the interpenetration, moving the objects out from within inside each other, and applying forces as necessary. Each worker, 1, 2, and 3, will decide that collision differently because of floating point math, because of dead reckoning models in between the servers. So those collisions are going to end up being calculated 3 times, and there'll be 3 separate results. On the next frame, the next time we've looped round and we're now doing the next physics tick, we already have the messages from the other workers with regards to where they think their entity belongs. Meaning that now we can use a standard distributed system election algorithm, and we can say something along the lines of, hey, I'm the worker that has the lowest entity ID within this group of colliders. So everyone take my opinion of this. So workers 2 and 3 can now go off and say, oh, well, actually, I calculated collision and it looked like this. The other process said it looked like this. Well, I'm just going to rewind and make it look like that. So you're never more than a frame or 2 out of sync, which means that you don't have to actually adjust rigid bodies, rigid body definitions. You can just use simple implementations like rigidbody.move2. Now, fast-moving objects colliding in the middle, obviously, to be honest, you can fake that on the client anyway, right? You can spawn some smoke effects, you can spawn some particles, and you can mask any inconsistencies. So it's actually not the hardest problem. The hardest problem in a distributed system is what we call achieving consistency. So in this video, we wrote a really bad load balancer, an incredibly inefficient load balancer that basically swaps entity authority left, right, and center almost at random. And then we started spawning a stack of 100 boxes, just 10 by 10, and then queued the load balancer to just absolutely trash itself. Now, the funny thing to note here is if the latency between these workers went above the frame step time, so if it went above 30 to 40 milliseconds, you'd notice that this stack of boxes would just vibrate itself to death and then eventually explode, because the number of collisions that were calculated and the level of variance between those solutions would actually just cause absolute chaos within the physics model, and it would just make them explode. But you can see here clearly that because of that internode communication being sub-millisecond, you do arrive at an eventually consistent model. And this is a big thing for a distributed system. The thing, and what you have to remember about SpatialOS is we always give you an eventually consistent view onto the world. And this goes into like the next step. Physics in the overlap working is great, but I think there's something to be said for distributed computing being so accessible now via SpatialOS that potentially there are other solutions. And so one thing that we're thinking about and we're prototyping at the moment is almost like a broad phase or what we're calling the network phase of a physics engine. Now, these aren't first-class terms in Havok and PhysX yet, because they're designed to be run on one machine and have complete authority. But using those ACLs that I mentioned earlier, what you could potentially build is a process that groups entities onto physics engines based on if they're likely to be colliding. So this is like a standard islanding algorithm. So you could use, I think this implementation that I'm showing you here uses Bullet Physics's BSP tree algorithm. So we're just partitioning the world up based on distance. And what this means is that we can start pushing entities onto the same process, ensuring that we don't have to do an advanced dead reckoning algorithm for collisions happening in the overlapping area. So this is, something that might become a first-class concept of SpatialOS, but it's definitely something to start thinking about when you're looking at distributing your game. So I know that was a lot of information, so I'll just quickly summarize what it is we've gone over. We spoke about the 5 key terms that SpatialOS uses. It's an entity component system. It is backed by workers, a worker being any process that links to our libraries. We use authority to move entities around seamlessly, and the thing that does that is called the runtime. We covered the idea of persistence, and I showed you that schema is the way that you define the messages in between for internode communication. We covered what a deployment is. It is an instance of your game world, potentially backed by multiple servers. And we spoke about code gen and the idea that from schema, I can generate you all of the networking code that you need to write your game against. And tools, obviously, we covered the fact that we do logs and metrics and snapshots as well. Cool. So next steps, obviously, the way we like to work out Improbable is we do a lot of game jams. And so just to cover some quick things that we've built, we have an open source RPG game that you can download available today. We spent 2 days trying to build a Fortnite clone, and we managed to get a couple hundred players in the world with a real-time construction algorithm. And my broad-phase physics worker that I mentioned earlier, that's also available as open source. There's highlighters for schema in Sublime. I have a microservice framework for writing really quick modular C++ services. And we've even started investigating dynamic language support such as Python and Lua. Using the C layer, we can make it so that without writing any new schema, you can start dynamically changing at runtime scripts such as LuaJIT and PyPy. So what's next is obviously you've got, you can sign up to SpatialOS now. We have lots of documentation available. You can join our community. The forums are super active. And obviously you can download that Sublime syntax highlighter. Awesome. Thank you very much.